What specific problem does the proposed method aim to solve?
The proposed method aims to solve the problem of reducing the memory footprint of the key value, KV, cache in large language models, LLMs. Specifically, the method focuses on decreasing the size of the KV cache by sharing KV activations across layers in the transformer architecture. By reducing the number of unique layers in the KV cache, the method addresses the memory overhead associated with storing and accessing the KV cache during transformer decoding. This reduction in memory footprint is crucial for efficient transformer-based language models, especially as new applications demand longer sequence lengths, which in turn increase the memory requirements of the KV cache. The method, known as cross-layer attention, CLA, offers a novel approach to optimizing memory usage in LLMs by sharing key value projections across layers, thereby minimizing redundant computations and storage costs associated with the KV cache.
How does the proposed method work and illustrate step by step?
The proposed method, cross-layer attention, CLA, works by sharing key and value activations across layers in a transformer model. This method reduces the size of the key value KV cache by allowing only a subset of layers to contribute to the KV cache, while the attention blocks in layers without key value projections reuse the KV activations of previous layers. CLA is orthogonal to existing methods like multi-query attention, MQA, and grouped query attention, GQA, and can be combined with them. The sharing factor in CLA determines how many layers share the output of each KV projection, with configurations like CLA2 sharing each KV projection among a pair of adjacent layers. By reducing the number of unique layers in the KV cache, CLA significantly decreases the KV cache memory footprint, leading to a more memory-efficient transformer model. Additionally, CLA slightly reduces the number of parameters in the model and the number of floating-point operations, flops, required during training and inference. It enables larger batch sizes and longer KV cache persistence times, potentially improving inference latency. However, CLA does not directly affect the core attention computation latency during decoding. Overall, CLA offers a practical and effective way to decrease the memory footprint of the KV cache in transformer-based language models, providing a favorable accuracy memory trade-off compared to existing architectures.
What are the theoretical or practical benefits of using the proposed method?
The theoretical and practical benefits of using the proposed method, cross-layer attention, CLA, include a significant reduction in the memory footprint of the key value, KV cache, enabling a more efficient storage and retrieval of persistent caches over long periods of time. CLA achieves this by sharing KV activations across layers, thereby reducing the number of unique layers in the KV cache. This reduction in memory footprint allows for larger batch sizes and longer KV cache persistence times, potentially improving inference latency. Additionally, CLA is shown to provide accuracy memory Pareto improvements compared to existing multi-query attention, MQA, and grouped query attention, GQA, architectures, with minimal degradation in perplexity. The method also offers flexibility in configuration, such as varying the sharing factor, which allows for customization based on specific memory budgets and model requirements. Furthermore, CLA is compatible with standard tensor parallelism techniques and slightly reduces the number of parameters and floating-point operations, flops, required during model training and inference, contributing to overall efficiency improvements in transformer-based language models.
How is the method validated or tested?
The method proposed in the paper, cross-layer attention, CLA, is validated through extensive pre-training experiments to characterize its impact on accuracy and memory usage across various architectural hyperparameters, learning rates, and model sizes. The experiments involve training transformer-based language models at both the 1 billion and 3 billion parameter scales. The paper compares CLA to existing multi-query attention, MQA, and grouped query attention, GQA architectures, demonstrating that combining CLA with MQA can achieve a 2x reduction in KV cache size with minimal perplexity degradation. The experiments also explored different CLA configurations, such as CLA2 and CLA3, to determine the most effective setups based on memory budget constraints. Additionally, ablation studies are conducted by combining CLA with GQA and exploring different sharing patterns of KV activations within the CLA framework. The results of these experiments show that CLA consistently enables favorable accuracy memory trade-offs compared to plain GQA or MQA models, especially when using a sharing factor of 2. The paper also conducts learning rate tuning experiments to verify the benefits of CLA, even when compared to baselines trained at optimal learning rates. Overall, the validation and testing of the CLA method are based on a comprehensive analysis of perplexity, memory footprint reduction, and performance across different model configurations and scales, providing robust evidence of its effectiveness in improving memory efficiency in transformer-based language models.
What results were achieved with this new method?
The new method, cross-layer attention, CLA, achieved significant results in reducing the size of the KV cache while maintaining model accuracy. Specifically, the paper demonstrated that combining CLA with multi-query attention, MQA, resulted in a 2x reduction in KV cache size compared to a plain MQA baseline at the 1B and 3B parameter scales. This reduction in KV cache size was achieved with minimal degradation in perplexity. The study also found that CLA configurations, particularly CLA2, which shares each KV projection among a pair of adjacent layers, performed the best in terms of accuracy memory trade-offs. Additionally, CLA was shown to be effective across different model scales, 1B and 3B parameters, and head dimensions, consistently providing memory overhead reductions with little risk to model performance. Overall, CLA proved to be a valuable method for decreasing the memory footprint of the KV cache in transformer-based language models.
What are the limitations or drawbacks of the proposed method?
The limitations or drawbacks of the proposed method cross-layer attention, CLA, include the fact that using sharing factors greater than 2, CLA3 and above, may achieve slightly worse accuracy memory trade-offs compared to using CLA2. Additionally, alternative CLA sharing patterns, such as concentrating all the KV cache-producing layers at either the beginning or end of the model, have been found to achieve worse perplexities than the corresponding models with a uniform sharing pattern, while also requiring slightly more KV cache memory. Furthermore, while CLA significantly reduces the KV cache memory footprint, it may result in a modest degradation in perplexity, although in some cases it can improve perplexity. Lastly, the effectiveness of CLA in improving memory efficiency may vary depending on the specific model architecture, learning rates, and hyperparameters used, which could limit its generalizability across different scenarios and applications.